Thank you very much. So we will start right away, and I must say we start in a glorious way, since we have the pleasure and the honor to have as our first speaker Reinhard Genzel, a very dear colleague of mine, who is one of the directors of the Max Planck Institute for Extraterrestrial Physics, and among many successes, he is a member of the National Academy of Sciences in the US and a foreign member of the Académie des Sciences. And in 2020, he won the Nobel Prize. And he will tell you about the project that made him win the Nobel Prize. Reinhard.
Thank you, Catherine. Dear colleagues, the science we are doing in astronomy nowadays has many aspects, very much in the spirit of the ESFRI, actually. It starts off with a bit like going into a forest you've never seen. You explore it, you see wonderful new things, trees you've never seen, flowers you've never seen. That's the exploration of the universe, which in astronomy, which is an old science, has nevertheless become tremendously exciting over the last 100 years. And then you discover that there are flowers in the forest, blue flowers, red flowers, and after a while, you note that the blue flowers are always on the left side of the path. This is when you change your profession, and you turn from astronomer to physicist, because now you would like to understand what in the hell caused the blue flowers to always be on the left side of the path. My story today is a story which is astronomy in its physics phase, so to speak. We're using the biggest telescopes which we have available, and I'll show you at the end that there's much to come, in order to test something which has been around for 100 years. That is general relativity, and the idea that gravity, when it's strong enough around a mass, can prevent light to emerge. That we now know to be a black hole. It showed up in the first solution, mathematical solution of the field equations, which Albert Einstein presented to the Prussian Academy in 1915, and 1 year later by this gentleman on the top there, Karl Schwarzschild. And that was the first of the several solutions of the theory, which is mathematically very complex. Another one was by the gentleman on the bottom right there, Roy Kerr, 50 years later, of an object which had mass and spin. Now, this fact that in these so-called black holes, on the one hand, the light might not come out is understandable because light sees gravity. That is experimentally tested and made Einstein famous. It was not clear that these objects actually would be realized, and there was much theoretical discussion for 50 years after the theory was published that this might be so. And Roger Penrose in the middle there, who shared the Nobel Prize with me, or I shared it with him rather, I should say, was the one who really showed that really, as if you have a curvature of space and time which exceeds a certain critical amount, you cannot but have a black hole. So a theory says these black holes should exist. But as physicists, we know that theory only means something if you can test it experimentally. And so are there these things called black holes? And in the 1960s, two discoveries were made which showed the first possible candidates. The first was very intense X-ray radiation from binary stellar objects. We now know that this is if you have a neutron star or a stellar black hole as one of the members. The one which I will talk today came about when radio astronomers discovered very bright radio sources in the sky, then looked it up in in the optical and found very faint star-like objects. You see there this little faint object, which, however, in spectra in the optical showed spectral lines whose identification was very clear, but they were all redshifted by 15%. That was a sensation at the time. Hubble had showed in 29 that the universe was expanding. So if you take that expansion rate and apply it to this redshift, this object must be 2.4 billion light years away. In the 60s, as I said, that was a sensation. And that means that that little light speck there emits more than 1,000 times the amount of energy the entire Milky Way does with, 100 billion stars. Yet it does it on a small scale. So how could that be? How could you generate so much energy, in particular also highly energetic radiation, X-rays, gamma rays, radio jets at almost the least speed of light emerging? Well, theorists thought about this in the 60s, and many of them, amongst them Martin Rees, Donald Lynden-Bell, Rashid Sunyaev, and others, came to the conclusion, paradoxically, that black holes could be the source of such energy. Why? How could black holes, which are supposed to be black, have the property of emitting light? Well, they are only black within a so-called event horizon, within which then communication to the outside world is not possible. Yet, if you have material accreting onto the hole at large distances, gravitational energy can be converted into heat through friction, probably magnetic friction, and then into radiation, such that between 10 and 40% of mc squared of a particle falling in can be converted into radiation. That's 1,000 times more efficient than fission and fusion. And so it's clear that if that mechanism actually holds, we might have in the universe some strange objects which can produce enormous amounts of energy. In fact, a single black hole, a massive black hole fed at maximum rate, can destroy an entire galaxy. We know that now. But how could you test that? Well, you use gravity itself. Like in the solar system, if you have the sun in the center and the planets moving around, then of course the motions of the planets on the orbits, on the circular or elliptical orbits, follows Kepler's laws. If you switch off the light of the sun, that doesn't change the planet's motion. So if you imagine another solar system where the sun is switched off, Tycho Brahe would have found the same orbital motions. So that's what we do too. We don't use planets, we use gas and stars, and try to find in the centers of galaxies whether there are some mass concentrations. We'd like to do it in quasars, of course, these very bright objects so far away, but at the time when this all started in the 1970s, that was not possible. It is possible now with an instrument I show you during my talk, but then it was not. So Lynden-Bell actually and Rees speculated that maybe these quasars are just extreme forms of highly accreting systems, and that maybe every galaxy has a black hole of millions to billions of solar masses, and only a few accrete very highly, but if everyone does, maybe our own galactic system might too. And there we can, of course, measure very much more precisely, because we are only 27,000 light years from the center. So that was the beginning. That was the recipe, and a number of people then started, and I'll show you the results. And the results in our galactic center is now that we are measuring with an incredible precision the motions of stars and gas, and we're pretty sure that there is a 4 million solar mass black hole. You heard already about gravitational waves, which also, remarkably, only 4 years earlier, had announced their first detection of gravitational wave from an in-spiral of one of these X-ray binaries, which I mentioned have stellar black holes in them. So that's the second avenue how you can actually test gravity. you use gravitational waves in an in-spiral system. And the third one is to actually use with very high angular precision the distortions of the light as it flies by and then it actually sometimes into the black hole with radio interferometry. All these three techniques are now being used to test general relativity 100 years after Einstein proposed it. That tells you that this field, strong gravity, is now one of the most exciting fields of physics and one which fascinates us all because it relates not only to our Milky Way in the presence of black holes, it relates to the evolution of galaxies, which sometimes, as I said, are controlled by the action of the black holes. And in a way, it points back to the Big Bang. It's a very fundamental kind of affair. So let's, however, reflect that these kind of measurements we are trying to do here are very difficult. We are trying to measure something like velocities to 10 to minus 5 of the value in order to see the effects well. Is that actually possible outside of a laboratory which you can control? Yes, we can do that now. We can do it, but in the galactic center, I should say, one of the problems is that optical light does not come out because of the absorption by dust particles. So we have to use infrared light. And when we started in the 1980s to do this work, there were no infrared imaging detectors. The American military had some because they wanted to see the exhaust from Russian rockets. Interesting disconnection. But then we were able to get some of that technology. Nowadays, I should say, we, the scientists of the European Southern Observatory and also my own group, are working with European industry to build detectors which are much, much better than the American detectors. Okay, so that's another example of the spirit of European collaboration, which you will see throughout this talk, which is a decisive thing and has brought Europe from a small player in the beginning of the story to a leading player at the current time. Another problem is the fact that if light from a distant source enters the atmosphere, it gets refracted and then by the winds distorted into a smeary image, which is much worse than diffraction. So it doesn't matter actually how good a telescope you have. And to overcome this, what we do is we measure the distortions and then have a deformable mirror in the path of the beam and undo the distortions of the atmosphere. That's a technique which was, again, developed in the US in the military in the 1980s for reasons which you can imagine, but then in France in particular, but also at ESO in the 1980s and 90s, and is now on every big telescope in astronomy. And so then when you start with this smeared out image and you switch on the adaptive optics, then you improve the sharpness of the images by factors anywhere between 10 and 100 and can make very precise measurements. Well, in order to do adaptive optics, you need to have a bright star in order to analyze the wavefronts, of course. All of this changes very quickly on kilohertz scales. Well, sometimes there are no bright stars near the objects you want to observe. Well, as a physicist, you go ahead and make yourself one. And so we shoot up sodium D lasers into the upper atmosphere, where there's a thin layer at 90 kilometers of sodium coming from meteorites. And those we can, basically illuminate, we can focus and generate resonant backscattering from a region, which then we observe from the ground, and that looks like an artificial star, and it's good enough to be used to correct the wavefronts. So this is to tell you that this kind of work, in fact, in my case, took 40 years. It was a journey of 40 years where we kept on improving instrumentation. And then at every stage, we came up with a good result, and then we asked our colleagues, so do you believe it now? And they said, oh, it's pretty good. No. That's science. So you have to keep at it. You have to keep at it and until you actually are successful. Now, I mentioned already the galactic center to which we are flying in now from the outer Milky Way has a lot of dust. You see these dust patches in the optical image, so it's hopeless actually to take a telescope and see the galactic center in the optical. So that's why we have to do this infrared technique, and indeed with modern telescopes and adaptive optics, we can look at the galactic center and see there an enormously rich and highly dense star cluster with millions of stars right in the middle, right in the very middle of our Milky Way. And that's, so to speak, these are our gravity test particles, which we are using to see whether there's something in the center. So that's a modern 10-meter class telescope images of the stars in the very center. These are very massive stars, I should say, not like the sun, so they're fairly bright. And in the center of it is a radio source, a very compact radio source, which was discovered in the 1970s, Sagittarius A star. And the radio astronomers over time have shown to us that the size of this object is a mere 40 microarc seconds. That's 20 centimeters on the moon, and about what you would expect from the outer so-called photon orbit of a 4 million solar mass black hole. So we've got an X marking a spot. So now we have to use our techniques, and okay, we have to work in the infrared. Initially, infrared, as I mentioned, was very hard, and the idea was to use gas. There's ionized gas. This is the pinkish stuff swirling around this region, and neutral gas, which is this green stuff. Now in Berkeley, where I then went as a postdoc, there was a very famous physicist, Charles Townes. Charles Townes got his Nobel Prize in 1964 for the invention of the laser and the maser. This is very interesting because you talked earlier about the intention for society to do something which is useful. So why are we doing astronomy? It's not very useful. It's exciting. It's good for the curiosity of humanity, but does it do anything for the betterment of society? Well, the laser actually does. As we know, nowadays it's the best timekeeper. You can cut metal with it. You can do operations with your eyes. So many applications. Well, if you ask Townes, why did you develop the maser and the laser? Well, you needed a lamp in the millimeter and infrared range to look at molecules. He didn't have any idea to use it for anything. Some of the greatest technological discoveries emerge from basic research intended for totally different purposes. And if you would have asked Charles Townes, please develop a system which you can use to cut metal, Charles would have said, oh, actually, I'm not that interested in it. Now, that might sound like arrogance, but the best minds are indeed often captured by very difficult basic research problems. Excuse me for this slight diversion. So Townes and his students, and then I joined as a postdoc, we started measuring the motions of the gas. And in this left diagram there on the vertical axis, in logarithmic units, you see the mass, which we can deduce from the orbits and from the motions of the gas. And then the the horizontal axis is the distance from Sag A star. And you see, when you're far out, the mass is large, and go in, the mass drops. And that's an extended mass. That's the stars. But then at some point, around a few light years from Sag A star, the velocities indicate that the mass is about constant, a few million solar masses. So in 1985, we wrote a Nature paper very proudly and said, we've got the black hole. Did we get any prizes for it? No, nobody believed it. Why not? Because gas can be pushed around by forces other than gravity, and we are, at this point, a million times the event horizon out from a central black hole. So there are many other solutions. Okay, back to the drawing board and improving the technology, and that is, in fact, using stars instead of gas, and using these new techniques, which I explained to you, big telescopes, adaptive optics, infrared detection devices, to measure the motions of stars and closer in. In fact, now we were joined by a group working with the Keck telescope, Andrea Guess and her colleagues. And so the two groups then proceeded in the next years, in the 90s, to measure the motions of stars, and by 96 to 98, we came out with our first results. And you see, in fact, the result there very clearly. If you put images from 3 different years in 3 different colors around Sagittarius star, which is that green cross, on a scale of a light month, which is that circle, then you can see that there is a star close to Sagittarius star, which moves with about 2,000 kilometers per second. That's 100 times the speed of the Earth around the sun. If you use Newton's physics on that and do v squared r over g to get a mass, you find a few million solar masses. So the same mass, essentially, we had already a decade before with gas, but now much more precise and further in. So were we done then? No. People were getting, they were getting impressed. At least the astronomers were. The physicists rather less. They felt, you're too far out. You still have to do more. So how could you have something which, how could you do better? Well, first of all, this is a statistical measurement of the average velocity. What you really would like to have is an orbit. Well, we knew the typical orbits in here are hundreds of years. That's longer than the lifetime of even the sturdiest Max Planck directors, so not so hopeful. But sometimes nature helps you. And that happened then in the next phase, that nature really was good to us. We were able to see stars which move on timescales which allow us to get their individual orbits over tens of years. On the left side, the best one until recently. On the right side, what both groups have then added in the next 10 years. Basically a universe of stars orbiting the central black hole on scales which brings them in their elliptical orbits. You see that on the left side. In 2002, that star went to about 15 light hours away from the black hole. 15 light hours is about 4 times the orbital radius of Neptune. So we're now on the scale of a solar system. The star was moving at about 2.5% the speed of light. You do v squared r over g again, and what do you get? 4 million solar masses. But now we are at 1,000 times the event horizon. And so now it's theoretically very difficult to imagine anything else but a black hole. Are we done? Well, a number of people proposed some alternative things, which I don't want to get into detail here, other than a black hole. The black hole seemed the most plausible solution, and some people said, well, how do we know that Einstein's theory actually is right in this mass range? It's well tested in low curvature. It's well tested in the solar system and in the laboratory, but not in these extreme situations. Well, that's a tall order. So in 2003, we thought about this and said, well, this star will come back 16 years later to the same point. It's an elliptical orbit. Then we must be able to measure, say, 20 times better than before. How do we do this? Well, we need a bigger telescope. And that telescope, in fact, we already had. ESO had on Paranal Mountain 4 telescopes, 4 8-meter telescopes, not just one. And there's a technique called interferometry, which radio astronomers know very well, where you bring the light from the 4 telescopes to a common point, interfere it there, and use interference to generate effectively a 150-meter diameter virtual telescope. And indeed, we were able to realize this under the leadership of Frank Eisenhower and a large European group with many of people in this room also present and leading it, France, Portugal, Germany, ESO. So that was a triumph of European cooperation, I would say. Nobody in the world has this instrument other than ESO. And it has done many more things other than the Galactic Center. It's a major breakthrough in instrumentation, 1,000 times more sensitive than anything else which was done. And so with this telescope, we can now go ahead and, in fact, resolve a Eurocent coin on the moon. And in this insets in the middle, you see we started 40 years ago with very unsharp infrared images. Then came the adaptive optics on the right side, upper right side. And then with the interferometer, we can go into the innermost little square there around Sagittarius star. And S2, that star which came back 16 years after 2002, we had then already observed. This is an image from last year. We expected not much. What did we see? A whole set of stars orbiting on scales of about 100 astronomical units with about 3–4% speed of light, like Times Square in New York. It's incredibly busy and fantastic to see all the effects which happen in these innermost dense regions. And it allows us to measure the motions of the stars now from night to night on scales of about anywhere between 30 and 100 microarc seconds. And that's really tremendously precise and precise enough to see the effects of general relativity. Now, the first effect you get to see is the so-called gravitational redshift. If a light source, like a star, moves through a gravitational potential and sends light waves to us, like a line, that light has to emanate from that potential, from that dense gravity, and gets shifted into the lower energy range. It's redshifted. So the light ends up at longer wavelengths than it started. And that's shown in the bottom. We're subtracting here in wavelength space the Newton orbit, which is the horizontal gray line, and the red is the predicted GR orbit, and you see the data follow GR perfectly. No doubt about that. Another prediction of general relativity is that orbits are not closed. In Newton, if you have a planet moving around a central sun and there's no other planet around, that orbit stays always the same forever, not in general relativity. One effect is this so-called Schwarzschild Procession. There's another one which has to do with the spin of the black holes called lens-tearing precession. So this Schwarzschild Procession predicts that the star S2 moves prograde about 12 arc minutes. That's 5 milliarc seconds per 16 years. And in the bottom you can see it. If you subtract again the Newton orbit in one coordinate, initially nothing happens, and then near Perry, all of a sudden the orbit makes a kink and follows exactly the red curve, which is general relativity. So we've bagged that too, but we're still 1,000 times away from the event horizon. So you could say, well, maybe the deviations from general relativity come in later or further in. But we have actually hot gas, which we can see when Sagittarius A star gulps some material every few days for a few hours. It turns out that produces hot gas, which orbits, and we can see the motions up in the bottom right for about 40 minutes. It's not a very long period, not very pretty, but it moves at a 30% speed of light there. 30% speed of light, and that's exactly, again, what you would expect from the so-called coordinate speed in general relativity. So we have several tests of general relativity, and they have all been passed. Now we want to do more. We want to measure the spin and test the fact that according to general relativity, only two parameters, namely the mass and the spin, are necessary to define an object as complicated as a black hole. That's remarkable. There are no hills on these objects. Two numbers, just spin and mass. That's a very strong proposal, and both the gravitational wave community and we will want to test that in the next years. Again, in this field, you have to stay healthy and stay at it for a long period of time. ESA will fly a mission, LISA, in 20 years, where hopefully the ultimate test will be done through laser interferometry in space. So we've come a long way in 40 years. Initially, we've seen with towns the first indications of the central mass, and then we moved inward with ever better technology, and now ended up close to the event horizon. And as I said, we have shown that in fact the potential is fit by a compact mass, which very likely is a black hole. In fact, the surprising thing is very little else is there. We can show that there is not a sort of an intermediate mass black hole or bunches of other things very close by, which is surprising. Many people would have expected, so to speak, astrophysically more action around. Now, the next big step is to go still bigger, and that's the ESO Extremely Large Telescope. So far, we've been using 10-meter class telescopes, but we are ambitious, and Europe has decided to attempt to build a 40-meter diameter telescope. Tremendous structure, the size of a football field. It's being built right now on Cerro Amazonas, about 25 kilometers away from Paranal, so very close to the current ESO site. And that telescope is a monster. When we started it, the Americans had also started on a 30-meter telescope, and it looked a little bit as if we would come in second, but now it appears that the strength of the European laboratory systems, the fact that we have very substantial activities of technology development at ESO, but also in France, in Germany, in other countries, has made it possible to be first. And I very much hope that before I see the flowers from below, I see the action of this telescope. My team, together again with colleagues here in France and others, are building the first instrument for the ESO ELT. That will be absolutely fantastic. Thank you very much.
Yes, fantastic. So thank you for this fantastic talk. I'm sure everybody was thrilled. And we have time perhaps for 2 or 3 questions, at least one, I would say, because it's... So, with all these lights I don't see, is there any question? Is there? I don't see.
Yeah, there's one up there.
I'm blinded by the...
Yeah, there.
So, the person who wants to ask a question,
Next to Guy.
Please hurry. Yes.
Thank you for this very interesting talk. So you have shown all the results from the evolution of the theory and the instrumentation. What role does take the computation in your field?
Well, it's very obvious that, for instance, let's take the adaptive optics. To do adaptive optics, you have to basically analyze the wavefront pattern on a scale of a millisecond and faster, and then make the computation of how you change the positions of the pistons on the deformable mirror. So in fact, that was a superb challenge in the 1990s, and the adaptive optics group here in Paris was certainly at the forefront of the world. Now we have even bigger systems. On the ELTs, we will have adaptive optic systems with thousands of pixels, and so that's really a tremendous challenge. And it's clear that in general, the detectors in astronomy are getting ever more sophisticated, and proper analysis of the signals is a real important thing.
Thank you very much, and I think in the end we really have no more time, so, oh yes, one quick question then.
Thank you very much. Just a simple question, I guess. What's your expectation of the effective impact of multi-messenger approach in astronomy?
Well, I mean, it's very clear that that's in electromagnetic waves already, I would say, very well realized between the different wavelength regions. That, you know, in one wavelength region you see very energetic light, but only at a given temperature range. In another waveband you see cool dust and so forth. And in the end, the universe is complex. Our forest is complex. It has different types and trees and so forth. Now with gravitational waves and actually also neutrinos in addition, of course, we get tremendous information. And I would say in particular the combination of gravitational waves and electromagnetic work is terribly exciting.
Thank you very much, Reinhard.
Should I leave this here or?
Yes, and I think you deserve one more applause because I'm sure everybody will remember this talk. And we now go to our first young researcher talk, and I invite Mark Visser from Radboud University, and who works on the European Social Survey, and he will present to us a medley of studies featuring the European Social Survey. Please.
Yes.
You have the time here.
Yep, sure. Thanks. Bonjour à tous. It's truly an honor to speak today in front of you, and also directly after a Nobel Prize winner. Really exciting. It also speaks to the diversity of today's event, I would say, not only in research topics, but also in career stages, actually. So also providing people in earlier career stages to present their research. So my talk will start from the premise that scholars have argued that surveys would be dead for several reasons, actually. First of all, decreasing response rates. So some groups are hard to reach. People would be tired of surveys. Maybe they're also a bit more skeptical towards science. So that leads to higher non-response rates and non-representative data. Another reason is that costs are increasing, or at least the cost effectiveness of these surveys. These are two often mentioned reasons, but probably the most prominent one is the rise of big data. So with real-time monitoring, gathering data from social media, the internet, surveys wouldn't be necessary anymore. But I'm actually here to tell you that, in my opinion, survey research is alive and kicking. So scholars have also argued that big data can be seen as an opportunity that complements surveys rather than replacing them. And this is actually also what studies have shown. So survey usage is actually increasing. Also big data use, but also the linkage between them. So that's actually good news. And I would argue even that it's now more than ever important to monitor social change. It's been referred to previously, pandemic, a situation in Ukraine. It's important to gather people's opinions and know how they behave. So I would say that surveys are still, at least in quantitative social science, the methodological vehicle of choice. And one of the big critiques of big data is that it's data mining, right? So it's not about testing theories. It's not about substantive research questions. It's looking at what's in the data rather than asking socially relevant questions. And that's where surveys come in. And it's especially thanks to initiatives like the European Social Survey that make this happen. So what is the ESS? It's a biannual cross-national survey that is still administered face-to-face, at least for the time being. And it was awarded ERIC status in 2013. So it's monitoring social change since 2002, but we're 20 years later now. So there are currently 9 waves, and the 10th is coming out in a few months, actually, the first data release. And I have to say, well, still in the early phase of my academic career, but for me, it's high-quality data and probably the best data I've ever used, survey data, that is. And this is because it's academically driven and quite rigorous, actually, in terms of not only design, but also data depositing, data documentation, and really front-running, I would say, in the world. So I've copied here 2 pages from the ESS perspective, so a bit of marketing. And you see here the enormous scope it has. So I think it was last week that I've read that it's now the ERIC institution that holds the most member states. And here you see the number of countries that participated at least once in a wave. And there are 38 now. 37 plus Israel. So that's pretty much all of Europe. And the way the European Social Survey is set up, it works with core modules and repeated modules. And these core modules are Ask Each Wave. So these are about politics, social exclusion, human values, the standard social demographics, and rotating modules. And these are really put forward by groups of scientists, social scientists, that produce proposals, and it's actually an open competition for who gets their items into this survey. And there are rotating modules on a lot of things: welfare, immigration, and most recently also, well, I would say core topic, climate change. So where's the music? I promised a medley. Before I come to that, a really small selection of my work. I've used the ESS data to look at financial hardship, especially between people in different labor market situations, that is, people working in non-standard versus standard employment situations. So usually standard employment is having a tenured or permanent contract, and pretty much everything else is non-standard. But I'm particularly interested in solo self-employed people and people on temporary contracts. I've worked on the fear of crime, and I've also picked up recently the topic of radical left voting behavior and support for radical left ideologies. So the medley. I'm really briefly, it's not going to do justice to these studies, but really briefly go through 3 of them. With a special focus on the role of the welfare state. So in the first study, I'm looking at the impact of the welfare state on economic marginalization. In the second study, again, the impact of the welfare state, but then on social participation. And in the third study, I basically connect everything. I look at the association between economic marginalizations, for instance, poverty, and social participation, and I examine cross-nationally whether this association is stronger or weaker in certain countries with different welfare state arrangements. Some empirical findings that align with these studies. In the first study, I've shown that, well, they're supposed to do this, but indeed, welfare states provide a social safety net that seems to alleviate economic marginalization. So that's good news, but maybe not that surprising. In the second study, which is actually in a long-standing tradition, it has been popularized by Robert Putnam, an American political scientist, who actually argued that in generous welfare states, people would be less socially active because they're not reliant on their social network and families anymore, but the government. The government gives them benefits, which means they would withdraw from society. And I have actually shown that this does not seem to be the case. It's rather a crowding in effect. So governments that are generous with regard to providing social security are actually promoting social participation. And this, for one reason, is of course because social participation sometimes costs money. but also it would set a proactive norm. Third, and finally, economic marginalized people are less socially active, which is in line with the idea of, for instance, having limited bandwidth, an idea in poverty research that people who are living in poverty are preoccupied with this daily making ends meet idea and do not have the space in their heads to do anything else. And I've also shown here that this differs across welfare states. So, concluding remarks, I would say that survey research in general, and in particular the European Social Survey, have a bright future ahead of themselves. And I would see the availability, the increasing availability of big data as an opportunity that will only strengthen that future. And it's also thanks to ESFRI that this is even possible. So I would like to close off with a new slogan for the ESS. So the old one was monitoring social change in Europe across since 2002, but I would say it's now monitoring social change in Europe for years to come, hopefully. Thank you.
Very good, very big change. I won't be able to ask questions, we are really too late, but thank you so much. What a wonderful also change of perspective. Well, we are 20 minutes late, and you know, eating is very important. So if we want to have lunch, we have to do something. And what I propose is that we move Philippe Bourges, the last talk, to the afternoon, which means that the whole meeting will start about 20 minutes later, or unless we gain some time on the coffee breaks. But I think it is better than to be running and also not to have time to have lunch. And so Philippe Bourges, like this, you know, you will speak after lunch, sorry. So the next speaker is Cotte, from the European Synchrotron Radiation Facility and CNRS, and she will talk about deciphering and preserving artworks thanks to synchrotron microscopes. Marine.
Thank you, Catherine. So good morning, everyone. So first of all, I wanted to thank the organizers for their kind invitation. If my presentation can be shown. Okay. So I've been invited to present some important application of the so-called synchrotron techniques to the field of cultural heritage. And through my presentation, what I would like to show you, beyond the examples, is the importance to create a synergy between a large-scale infrastructure and a user community. So 20 years ago, I was completely new to this field. I was then a PhD student at the Center of Restoration and Research of French Museums, which is a lab in the basement of the Louvre Museum, next to here. And the general goal of this research was to get insight into chemical, pharmaceutical, and medical knowledge and practices in antiquity, thanks to the chemical analysis of ancient cosmetics and drugs, as well as the analysis of ancient recipes. Fortunately, some of the ancient cosmetic spots conserved in the Louvre Museum still contain cosmetic powders. And by chance, we were allowed, here it is, we were allowed to sample very, very tiny fragments from these cosmetic pots for some chemical analysis. So chemical characterization can be performed with standard laboratory techniques. However, technical challenges in this case are many. When fragments are sampled, they are extremely small. So for example, here the particle has a size smaller than the diameter of a hair, and also very precious. So non-destructive techniques are usually favored. And these samples are also extremely heterogeneous and extremely complex from a chemical point of view, being made of, for example, mixture of organic, like fat, and possible various inorganic compounds, such as pigments. So in order to obtain a maximum of chemical information of very high quality and non-destructively, my supervisor proposed me to go to a synchrotron facility. So what is a synchrotron facility? This is more or less like a donut with at its center a linear accelerator and a booster which will create and accelerate a beam of electrons. When the electrons have reached a sufficient speed, they are sent into the storage ring, and there, under certain circumstances, when electrons are submitted to a magnetic field, this interaction will lead to the tangential emission of a so-called synchrotron light. This light has many properties. In particular, it is bright, meaning intense, small, and collimated. It is polarized and multicolor, covering mainly from infrared to X-rays. And this kind of beam is perfect for microanalysis. And using the various properties of the beam and different detectors, complementary techniques can be carried out with synchrotron light, offering a panel of chemical contrast. Worldwide, there are about 50 synchrotron facilities, most of them being national instruments. In Europe, we have the chance to have a European Synchrotron Radiation Facility, so the ESRF, which is in south of France, in Grenoble, and which is funded by 22 partner countries. So to give you an idea, the circumference in this case here is 840 meters, so it's really large-scale facility. So the path from a scientific question to a synchrotron experiment can be long and difficult. First, users must submit a two-page document which is reviewed by an external panel based on its scientific excellence. And then only one proposal over 2 or 3 is accepted. In this case, 6 months to 1 year later at best, beam time is given for 1 to 6 days, 24 hours a day. Then users come to the SRF with their samples, or we now offer remote access as well, and perform the experiment. So this access is highly competitive, usually favoring expert users and innovative experiments. Consequently, it is a particularly challenging environment for the cultural heritage community, where there are not so many expert users and where routine experiments are usually sufficient to address important scientific questions. However, despite these conditions, there is an increasing number of applications of synchrotron for the study of our cultural heritage. In this slide, I selected only a few of them to show you the variety of materials and objects which can be analyzed. So as you can see, paintings are the most frequent materials, but we can also analyze glass, ceramics, papyri, plastic, or even modeling clay, as in the case of the sculptures by Rodin. Second, the fact that these samples are coming from all over the world. For example, this painting by Matisse is from an American collection. Also, users are coming from all over the world with a favored access to European users. And finally, scientific questions can be sorted in 2 classes. Those which target the production of the objects, so which materials were used, if they were natural or synthetic, what were the firing conditions for the glasses and the ceramics, and so on. And those questions focused on the conservation of the objects, where chemical analysis aim at understanding and assessing degradation phenomena and identifying the parameters, for example, light, humidity, pollutants responsible for this degradation. So this is in particular the case for the sunflowers and the scream painting. So choosing few examples in this list was not easy, and I have selected 5 of them to give you an idea about the various scientific questions and chemical information obtainable via this synchrotron analysis. So in the first example, I come back to the Egyptian cosmetics. Results were many, and the most striking one was the identification of exotic lead compounds, which are named laurionite and phogenite, which demonstrate a very early use of what we call wet chemistry, meaning that you manage to synthesize the products at room temperature, working in aqueous solution at low temperature. We could also determine that some of these lead compounds were chemically associated with organic materials under the form of lead soaps, similar to the sodium soaps that we use every day to wash ourselves. And this was in very good agreement with medical recipes from antiquity, from Middle Ages, up to the beginning of the 20th century. In the second example, we stay in ancient Egypt, but the material is completely different. In this case, we were interested in understanding the composition of inks present on ancient papyri. The invention of ink is essential for humanity. It was fundamental to give the possibility to preserve and transmit human thought and knowledge on a flexible and durable material, the papyrus. During the past decade, many scientific studies have been conducted to shine a light on the invention and history of ink in ancient Egypt and more generally in Mediterranean cultures. However, many of them are limited to very few limited papyri. And in this study, we investigated the composition of red and black inks inscribed on papyri from the only large-scale institutional library known to have survived from ancient Egypt, the Tepnubis Temple Library from the Carlsberg collection in the University of Copenhagen. This research project was exceptional, not only due to the provenance of the papyri, but also because the analysis included as many as 12 ancient Egyptian papyrus, and all described with both red and black inks. So we used synchrotron microscopy to zoom in and analyze at increasing resolution. Unsurprisingly, iron, here in red, was found in the red ink, which corresponds to ochre, which is a natural iron oxide pigment. Much more surprisingly, lead, so here in blue, was detected in many inks, and both in red and black inks, and revealed a very peculiar distribution around the ink letters, and also diffusing within the cells of the papyrus at high resolution. Chemical analysis revealed that lead was associated with many compounds like chlorides, sulfates, phosphates, but also organic compounds, as highlighted by the detection of lead soaps again. All this information let us think that lead compounds were not used as pigments, so to give a color, but better as dryers, meaning to accelerate the drying process of ink. And interestingly, the invention of oil painting relies essentially on the use of dryers, in particular lead-based dryers. Europeans usually consider that oil painting was invented in Europe in the 15th century. However, analysis carried out at the ESRF in 2006 demonstrated a much earlier use of oil painting in the Middle East, from the 6th to the 9th century. This work was carried out on fragments from the wall Buddhist paintings from Afghanistan, from Bamiyan, which is a site which is well known, unfortunately, because it is where there were the big Buddha's statues destroyed by the Taliban. UNESCO asked the National Research Institute for Cultural Properties in Tokyo to lead research on the Bamiyan wall paintings to better understand how they had been produced, particularly in connection with other artistic practices along the Silk Road. So we combine different synchrotron techniques, and this revealed the presence of various pigments, degradation products, but more importantly, we detected oil, as you can see here in some of these layers. And on top of that, the fact that oil had been treated with lead dryers, similarly to the Egyptian inks and cosmetics. For the first example, let's continue to talk about oil painting, but in a period and place closer to us. In this case, colleagues from the Rijksmuseums were interested in better understanding Rembrandt impasto technique. So Rembrandt invented a unique way to thicken his oil, such that he could work his painting material as a volume and not as a flat surface, as commonly done. So the question was, is there a chemical signature in the impasto layer which could give or reveal the way Rembrandt obtained his impasto technique? For this analysis, we got access to tiny fragments from 3 paintings by Rembrandt and from both the impasto and non-impasto regions. And surprisingly, we detected systematically and exclusively in the impasto regions a very unusual lead compound, which is named plombonacrite. And for us, the presence of this plombonacrite can be associated as a secondary product of the treatment of oil with a lead dryer. And by reproducing contemporaneous recipes to prepare second oil, we could observe a similar presence of plombonacrite in our model paintings. And just for the anecdote, the reason why oil thickens is because of the formation of lead soaps again. The last example has nothing to do with oil or with lead soap, but it's probably the closest to my heart. For this work, I was contacted by a colleague from Center of Research and Restoration of French Museum, and she was analyzing very early color photographs named heliochromies. She was reaching the limit of her laboratory instruments, and she asked me if synchrotron techniques could help getting information about these photographs. I proposed her some help and started to discover the extraordinary life of Louis Ducos-Duron, the person who invented the methods and produced these photographs. This person has been crucial in the development of photography, color photography, among other developments, but never managed to propose a commercial solution, and this is probably why his name has not been written by history. He was fundamentally motivated to make his discoveries accessible to anyone, publishing books with very detailed instruction, breaking patents quite early. In this study, it was amazing to establish links between his text and the synchrotron analysis of the very tiny fragments from his heliochromies, and to see how his methods evolved towards lower cost, higher efficiency, and stability. And I'm very happy to be able to pay tribute to him in this prestigious place. And if you read French, I really advise you to go on the Google and have a look at his book, where much of them are available, and it's really, really fascinating. So after this example, let's come back to infrastructures. Over the last 12 years, the ESRF has benefited from a major upgrade program, as shown by comparing these two pictures taken in the 19th and more recently. The ESRF program phase 1 was dedicated to the installation of 90 new beamlines specialized on nanoscience. During phase 2, which has been renamed EBS for Extremely Brilliant Source, a new generation of synchrotron storage room was installed and will be complemented by 4 new beamlines and 7 refurbished beamlines. And on top of that, efforts have been dedicated to develop detectors and instrumentation, as well as information technology data strategy. In September 2018, ESRF EBS was confirmed as landmark in ESFRI roadmap, and this has been very beneficial in the context of the upgrade. So what does that mean in practice, the EBS and an extremely bright beam? So if I come back to the Bamiyan painting, here you can see two maps, one acquired in 2006 and one which was acquired last year. Both of them were acquired on the same sample, or the same painting, two fragments, and the results are shown with the same scale. So these images, they are a distribution of pigments and degradation products. You can see that this one was acquired faster than this one, but has a much larger field of view. And if I zoom in so that you can better see the small map from 2006, you see also that this one has a much better resolution. So in practice, EBS means that we can analyze more samples with larger fields of view, with higher resolution, and so in total with better statistics. So as illustrated here, the new source, the new and refurbished beamlines, and the new techniques will permit acquiring more data of better quality and higher complexity. However, for the sustainability of the ESRF, this tremendous improvement in data collection requires to rethink the entire workflow, taking into account both upstream and downstream bottlenecks. Faster experiments means that potentially we could welcome more users, new users, and more diverse users, providing we implement new access models. I will come back to that. We identify emerging scientific communities, and we develop a sufficient outreach program for both academic and industrial users. More sample and more diverse samples require a dedicated sample management system and new sample environments for high throughput. And to better convert data into scientific results, new tools for data collection, new workflows for data online analysis and machine learning routines are required that will increase the results quantity, quality, and fairness. In the context of the call H2020 InfraDev, the ESRF has received a grant to tackle these many challenges. So regarding the access model, if an experiment which was typically carried out over 4 days can now be carried out in few hours, you can easily understand that the standard 2 pages proposal is no longer well adapted. So as an alternative, we propose to explore an access which has long been used by the protein crystallography community, the block allocation group access. In this case, several users who share the same technical needs and who would need only a few hours per year for their analysis, submit a unique joint proposal and manage between themselves the distribution of beam time. 3 of such bag access has been pioneered last year at the ESRF, among which one for the cultural heritage community. And honestly, this is a real success, a huge success. We have now 11 European teams working together and making a very good and synergetic use of the ESRF. And I would say that beyond the logistic benefits, in particular for the ESRF in terms of proposal evaluation, scheduling, and so on, The outcome for the community is in terms of trainings, in particular of young students, and the development of network is absolutely impressive. So I think it's certainly the best way to strengthen the cultural heritage activities at Synchrotron. Before concluding, I would not like to let you with the idea that synchrotron facilities are used only for cultural heritage, and indeed this community represents only a few % in the middle of many fields such as health, medicine, food, energy, environment, fundamental physics, and so on. And with this, I warmly thank you for your attention, the organizers for their kind invitation, our colleagues and users involved in this research, and of course Europe for its support in our facility. Thank you.
You all enjoyed, like me, this fantastic presentation. It was really great, Marine. And since we decided not to have the next talk right now, we can have time for a few questions, if there are any. I'm still blinded by this. Does anybody wish to ask a question? Yes, please. Can somebody give him a...
Thank you very much. It was really very nice presentation. But I have a question, well, maybe easy or difficult to answer. But how you deal with the uniqueness of the object that sometimes you want to try or to measure, because are very difficult to transport, very difficult to get permission from the owner, I would say, because it's so precious that are really unique in that sense. So how do you deal with this issue?
Very important point. What I'm doing is microscopy, so most of the time I work on very small fragments. But it's true that in other cases, for example, in paleontology, they work on entire objects. And so they need to bring the entire fossils or at the ESRF or at a synchrotron facility. So that's critical, and it's true that it requires a good management, insurance, and so on. But it's feasible. So the idea is, as much as possible, to first to limit the, let's say, information about that, such that people know that such precious objects were at the SRF after the experiments and not before. And also there are, for example, ways to ensure the conservation of the objects in good conditions. So that's something which is taken into consideration. But for what I'm concerned, most of the time we work on fragments, so that's much easier, because they are extremely small, yeah. Yeah, just
okay. Any time for one more question? If there...
No need to. Thank you. That was a very beautiful talk. Thank you. I was wondering with fossils, and to what extent you can use the same technologies that you've described here to analyze some of the ancient things that we have in our Natural History Museum, and how much of that happens at the ESRF.
There is indeed a very, very active program in this domain, in the domain of paleontology, so active that one specific beamline was built first for tackling this community of large objects and tomography. So the possibility to see detailed structure on large and heavy objects, in particular fossils, but now also this beamline is found interest for also applications such as medical application as well. So it's true that what I've shown here was mainly about chemistry, microscopy to tackle the chemical composition, but it's true that on the side of imaging, there are lots of applications in the fields of natural heritage, let's say. Yeah. So both of them are very, very complementary.
Thank you very much. I think we'll have to stop here. Okay. And we have the pleasure of listening to Philippe Bourges from CEA, the French Alternative Energy and Atomic Energy Commission. And he is going to talk about neutron diffraction and spectroscopy at the next generation neutron source, ESS. It's interesting, there are two ESS in ESFRI. I'm sure you all noticed. So nothing to do with the previous one. Please.
So here, ESS is meaning European Spallation Source, so they're very different. So first, I would like to thank l'Académie des Sciences and ESFRI to give me the opportunity to present neutron diffraction and neutron spectroscopy. and in particular the next generation neutron source, which has been promoted by ESFRI. So here I show a view of the ESS site from last December, and you see that the construction is going well. So the neutron beam, so what's called the neutron on target, will be in 3 years from now. So my talk will be in 3 parts. So I will show how neutrons are unique to study condensed matter. And I will show also how ESS will be the most powerful neutron source in the world. I will, as the subject of neutron diffraction and neutron spectroscopy is quite vast, I will limit myself to the topic where I am working on, which is high temperature superconductivity. And at the end, I will show some example of instruments which are to be built at ESS for that type of science. So neutron is a neutral particle which can interact with matter and can easily penetrate into the matter over a few centimeters without damage. And because of that, we can do neutronography of a microscopic object. Here I show an example of a Buddha statue. So the interaction of neutron is with what we call hard matter, so the solid state science, but also soft matter, which correspond to physical-chemistry or biophysics or life science. So at the difference of X-ray, where the interaction strength is proportional to the number of electrons of atoms, neutron can be very strong scatters of light atoms. That's the case, for instance, for hydrogen and deuterium. So we can study many life science materials. So there is also another interaction of neutron, in addition to the interaction with the nucleus of atoms, which is a magnetic interaction, because a neutron carry a magnetic moment, what we call a spin, and then we can have information on the magnetic properties of different materials. And that's what I will show here most likely. So typically, neutron, there is a lot of observable with neutron scattering, because for the neutron which has a wavelength which is of the order of distance of interatomic distances in solids, it has a kinetic energy of the same order of excitation in solids. So then you can do space and time studies simultaneously. And that's very important, and that's true for both structural and magnetic properties. And here I show, for instance, I show a structure when we call diffraction. You just study the structure, which means the average position of atoms. And I show also excitation. In the down part, I show phonons, so the lattice vibration. So we see atoms who are moving around the average position. And also for spins, there is also some excitation. Here we see a line of spins which are waving. We call it a spin wave. So here I show a chart of all the possible application of neutron, and you see it impacts all condensed matter physics and chemistry. And so ESS will allow to go faster experiment to study more complex chemical and physical systems, and so typically to do experiments which are not possible at present. So here I show a plot of a brightness of neutron versus time in a logarithmic scale. So typically, historically, the neutrons are produced by a research reactor, by a nuclear reaction. Here it's an orange curve here. And that's the case, for instance, at the European neutron source ILR in Grenoble at present. It was also the case at the reactor Orphée, where I was working during my career. So I show here the two reactors on this graph. But the technology to produce neutron at ESS will be different. It will use the spallation reaction, which is you send an accelerated proton beams onto a target. It is tungsten, and then it produces a lot of neutrons, about 20 to 30 neutrons per proton. And this way you can have a much higher flux. And that's why ESS will be a very high, very powerful source. And I show ESS here at the end of the plot. Also, neutron produced by a reactor, it is a continuous source. But due to limitation of the heat power on the target, the spallation source will be a pulse. And so you have not continuous measurement, but pulse measurements. And I show here the shape of that pulse, and you see that ESS will be world-leading. You sense that pulse is much broader, so it's 3 milliseconds long. It's much longer than other sources which are shown here, and also higher in amplitude. Also, the repetition rate, so the frequency at which the pulse will arrive, is much larger than a conventional source. Also, as it is a pulse source, it's possible to use the time-of-flight technique to measure the neutron, to detect the neutron. And so this way, it will be a much higher intensity, but because there is a recent progress in neutron instrumentation. Okay, so here I show a panorama of complexity and sensibility of measurements or experiments done with neutron scattering over years. So you see that we can study in all different types of science, from let's say biology to hard matter. And you can see now we have more and more detailed picture of the physics and the chemistry of a system. So typically I will speak about the right side of a slide here, where we use polarized neutron to study magnetic correlation. So my domain of research is superconductivity. It's a fascinating properties where there is zero resistance at low temperature. And there is also some magnetic levitation, as I show here in this figure. And not less than 8 Nobel Prizes has been given on that topic since the discovery of a phenomenon in 1911. It was done at the time on the pure mercury system. The only limit is the fact that this phenomenon occurs only at very low temperature, so typically 4K above the absolute zero. It took about 50 years to have a good theory for it. It's called Bardeen-Cooper theory, BCS theory. So all this picture has been challenged in 1986 by the discovery of a high TC superconductivity in copper oxide, where TC can reach 135K, so much larger value. And the structure of that compound is very different. Inside it's a 2D system with a stacking of copper 2 layers. So superconductivity is you can have a lot of application for that for energy transport or energy storage, using the fact that there is zero resistance. Also, you can build electromagnets, which is the case, for instance, for magnetic resonance imaging for medical purpose, and there is also some application in electronics. So coming back to the fundamental physics of superconductivity, so the BCS theory is saying that the electrons are forming pairs that we call Cooper pairs, and so and that because of interaction with the phonon, which is a lattice vibration. And as I said, neutrons are playing an important role to verification of that theory in the sense that neutrons can measure directly these phonons. For the copper oxide superconductors, we don't know the interaction. There is no consensus on what is the interaction to which is explaining that. There is some proposal that this can be related to magnetism, to the fact that the electrons on copper side carry a spin. And I will show some example of that. And the role of neutron will be to detect novel and weak magnetism in relation to that. So as I said, the building block of a copper oxide superconductor is a copper oxygen plane that I show here, where each copper is carrying a spin, shown here in red. And the interaction between first neighbor is antiparallel, so what we call antiferromagnetic. Actually, this picture is what we know from the measurement, especially from neutron scattering, but this picture is not static, it's dynamic. So in the real materials, this is a dynamical effect. And that's shown that measurements like that, where we have neutron intensity versus wave vector. So wave vector is in reciprocal space. Reciprocal space is a dual space of a periodic lattice of atoms. And otherwise, the same way that using telescope, you can see stars in the sky. Here, with neutron spectrometer, you can see bright spots in the reciprocal space. So it's not our real space, but some dual space are related. And the originality of that excitation is the fact that it disappears with temperature, and it disappears at the superheating temperature, and that's considered as a direct manifestation of a glue of a high TC superconductivity related to magnetism. So that ITC copper oxide superconductors has been studied a lot. It's the most studied system in condensed matter because it has a very complex phase diagram when you have a superconductivity, which is here in purple, and you have two mysterious phases, the pseudo gap and the strange metal, that we cannot understand, which is not understood 35 years after. So we address that problem with a new state of matter, something very original, very exotic, which is a current, as shown by this animation here, which is current between copper orbitals and oxygen orbitals. So there is this microscopic current, okay, and that state, which is very exotic, breaks some symmetries that we can test with neutron scattering. So we believe that state is the origin of underlying physics of the cuprates. So the source of magnetism classically are the orbital moments of electrons around the nucleus, or the spins of electrons that I was also mentioning. So loop currents would be a third example of that, in the sense that you have the closed loop currents are producing magnetic moments with two opposite orbital moments, like is shown on this picture. So this way, neutron can measure this state. So there is so this loop current is forming a network on the copper oxygen layer, and so we have scattering from the lattice and scattering from the loop current at the same position in momentum space, in the reciprocal space, and so you need to use polarized neutron to be able, where we control the spin of a neutron, to be able to separate both signal and measure both systems at the same time. So that's what we have done. And that's our measurement here of a normalized neutron intensity versus temperature. And you see there is some increase at low temperature, meaning that we have this new state, and that's very consistent in terms of symmetry, which are broken here, consistent with the loop currents ideas. Recently, we have been showing that actually another type of magnetic correlation exists as well, and meaning that the story is not finished yet, and there is other flavors of loop currents. I should also mention that there is these loop currents are also generic to other correlated electron system, in the sense that we observe the similar type of signal in other systems. So it's more generic than it was first thought at the beginning. So what ESS will bring to that science? So I show here the implementation of instruments at ESS. So there is the target, which is the red point here, which is heated by the proton beam. And you have two main holes of an instrument, a short one and a long one. The long one is making 160 meters long, so it's very long. And so, as you can see by the flag here, it's a work in collaboration between many different countries, and France is involved in five of these instruments. And typically, most of these 15 instruments will be ready in 3 years, when the first neutron will come onto the target. So I show here the instruments where we will be able to study magnetism. So, and I will show more specifically two instruments on which I have been working. So, which are Bifrost and Magic. So Bifrost is based on a novel concept. You have a drawing of instruments here. So it's a long instrument, so it's 160 meters. So you need to have neutron guides to carry the neutron, and that was possible because there is a recent progress in these neutron guides without loss. Also, because there is a long distance, it means that there is a distribution of neutron wavelength and energy when at the sample position. So this way, even if the source is pulse, actually at the sample position, and so at the detector position, the measurement is continuous. So that's why it increases a lot the intensity we can get at the sample position. Also, it was the secondary part of the instrument, so after the sample, it's also based on the multi-detector, multi-analyzer system. So it's really doing much more, you can measure much more neutron at the same time. And we expect to have something like 3 orders of magnitude larger intensities than existing instruments of the same way. So that instrument will be capable to do the science I was mentioning before, to study excitation, to work on much smaller samples, and also to increase the capability, because we will be able to also to measure high pressure cell, so high magnetic field. So typically we'll be able to see the spin resonance peak that I was mentioning. So Magic is a polarized neutron diffractometer at ESS. So it's built by 3 partners. So France is the leading partner for that instrument. And typically I show here what we call the experimental cave, a drawing of that, which is a few meters size, just to give an idea. And so the instrument, which is on the left side, will fit inside that cave. And so you see in blue, you have the cryostat, so where the sample is put, and you have on both sides banks of detectors which will do all the needed purpose to use polarized neutron to do the best experiment possible. So that instrument also will be much more efficient than the existing instrument at the moment. So all these instruments will study magnetism in all forms that you can imagine. So I can give you example of about spin liquid. There is many examples, or for instance, to study thin films, which are important for electronics or spintronics. And that instrument MAGIC will be very important to study this loop currents, to have the detailed form factor, structure factor of a phenomenon, and prove that it's really the only way to interpret the data. So I've been showing that neutron ISS will be a wonderful feature, will show a wonderful feature. It will affect many aspects of science. So for instance, the soft matters, it would be important for food and drugs industry. Or for instance, also in hard matter, it will be important to study batteries for electric cars, or solar cell for photovoltaic materials. I've shown my own result about superconductivity, where we have established this loop current state. So clearly, ESS will be starting in about 3 or 4 years from now. Will bring wonderful science on new materials with novel properties. Thank you.
Perfect. Thank you very much, Philippe. So are there questions? Ever see? Yes, I see a question there.
This is not rather a question, it's a small remark. To this 20th anniversary, I just would like to mention that one of the first actions of ESFRI was to set up a working group on the ESS. And this working group made a recommendation that this new spallation source should be a long pulse source, not rather than a short pulse source like the other ones. And Ferenc Mezei, my colleague from the Budapest Neutron Center, published these results a few years before. So this is just to remember the anniversary. Thank you.
It was a very good decision. I mean, but it's also a big challenge, because we have to do the instrument. I mean, the instrument very differently to improve the neutron instrumentation related to that. But at the end of the day, it will be very, very good indeed. Yeah.
Yeah, I also remember that very well, I must say. I also chaired the committee to help look at the sites, and actually 3 excellent sites were proposed, all of them excellent, intended up in Sweden, as you all know. Okay. The other 2 sites, including one in Hungary, would have been excellent as well. Yes. Okay, are there any more questions? If not, this is the end of the first session. So I would like... Oh, sorry, I didn't see it. I don't know where you see something. I can't see anything with these lights.
I'm waving.
So we'll have another question, and then it's the end of this session.
Yes, thank you. In 2016, ESFRI published the first ESFRI scripta, and that was about the neutron scattering landscape and foreseeable landscape in Europe, having the ESS under construction and lasting for some time. Maybe in 2016 we were expecting a quicker startup, and seeing the progressive dismission of the other neutron sources. Now the ELL has been prolonged, but still we are in a situation in which at this very time there is a shortage of neutrons. And what is your overview of how much and in what delay from day one, when only a few instruments will be operational, the ESS will catch up? And do you see a role for other regional sources to replace those that are being dismissed?
It's a big question. Indeed, there will be a shortage of neutron in Europe compared to the situation at present. And I think that's important to have also local sources, indeed, based maybe on different technology, but there is a few projects around Europe of a compact source, which can play an important role. So I think that's important to keep an eye on that, because ESS, I'm afraid, won't be able to produce enough science. You can do more, indeed. Yeah. Thank you.
Thank you very much. So we thank Philippe again.